Hi, my name is Andy Murphy, and my co-authors are Irena Yanushevskaya, Ailbhe and Gobl, and we work in the phonetics and speech laboratory in Trinity College Dublin. And I'll be presenting our paper, testing the GlórCáil system in a speaker and affect voice transformation task. So first, the outline of this presentation is as follows. I'll start with a brief introduction of the work and why it's important to the ongoing research and application development in our lab. I'll then go on to describe the GlórCáil analysis and synthesis system, followed by how we tested the system using a manipulation-based listening test. Finally, I'll finish with conclusions and a mention of some future work. So having flexible and expressive speech synthesis is useful in a whole host of different applications. Here I'll describe a system that allows for the transformation of voices using an acoustic glottal model-based excitation. This transformation allows us to introduce expression into synthetic speech by manipulating the voice quality of an utterance. And this work is part of the Irish Synthesis project, which requires flexible and expressive synthetic voices for use in ongoing application development. These applications include those for users with disabilities, such as visual or voice impairments, for research tools to further our knowledge of linguistic and paralinguistic prosody, as well as in Irish language learning applications, such as interactive multimodal educational games. So we have a limited number of synthetic voices at our disposal. So having the ability to generate a character with, say, a happy voice or a grumpy voice to suit particular scenarios within the games is a major benefit. Another factor that must be taken into account is the complexity of the voice source and how to control it. And there are a multitude of different parameters that can be used to describe the source, but it is desirable to simplify these as much as possible so that easy control of the source can be obtained. We found in earlier studies that the global wave shape parameter RG can be used as an effective control for both linguistic and paralinguistic prosody. So RG is the global wave shape parameter of the LF model. It's derived from F0, EE, and UP, where E is the excitation strength, and UP is the peak flow, the global pulse, and variation in RD is proposed to reflect voice source variation along the tense lax continuum. The values typically range from between 0.3 for very tense voice to 2.7 for very breathy voice. So now that I've gone through some of the background, I'll describe the GlórCáil system itself. I'll start by explaining the name. It comes from the Irish words glór and cáileacht, meaning voice quality, or something close to that. It's hard to get a direct translation. It's implemented in MATLAB and has three main components: the analysis stage, the synthesis stage, and the user interface for controlling the synthesis parameters. A brief overview of the processes involved are that first, vocal tract and voice source parameters are estimated in the analysis stage. These parameters can then be manipulated in the interactive graphical user interface, and speech is then resynthesized using an acoustic glottal source model, in this case the LF model, in place of the original glottal source. User can listen to results of manipulations and make further desired changes to the perceived voice quality of the utterance through the interface. Alternatively, the system can also be integrated into an existing TTS framework in order to manipulate novel synthetic speech. So here we can see a schematic representation of the analysis and synthesis stages with the interface used in the experiment described in this paper, but this interface could be changed out for one with different controls depending on the desired application. I'll first describe the processes involved in the analysis stage of the system. So the speech signal polarity is checked and corrected if necessary. F0, GCI locations, and voice-unvoiced regions are estimated. Then inverse filtering is carried out on a frame-by-frame basis using the GFM IAIF method, but substituting discrete all-pole modeling in place of the usual LPC, as it provides a more accurate estimation of the vocal tract transfer function. We now have the vocal tract filter coefficients and the differentiated glottal flow. So the next step is to transform the filter coefficients to line spectral frequencies, as these are more robust to processing techniques and statistical modeling methods employed in TTS systems. Then the LF model matching is carried out on the differentiated glottal flow signal in order to extract a set of source parameters. So I'll just skip the description of the user interface for now and go on to describe the synthesis stage of the system. So the user can transform the extracted source and vocal tract parameters using the interface. The voice excitation is generated by concatenating LF model pulses with the addition of amplitude modulated white noise. The LF model pulses are calculated based on the RD parameter that was mentioned earlier. So F0 is used to determine the period of the pulse, and this is used to define the start and end points of the pulse frame within the voiced excitation. The parameters EE, RD, and F0 are used to generate a full set of LF model parameters, and these parameters are then used to generate the corresponding LF pulse. Amplitude modulated noise is added to the pulse, and then the next pulse is calculated using parameter values from the closest frame to the end of the previous pulse. This process continues until the current voice region has been filled with pulses. The pulses start and finish at 0, so no windowing is required to prevent discontinuities in the signal. So frames with values outside the F0 thresholds are treated as unvoiced regions, and white Gaussian noise is used as the excitation signal in these areas. The generated excitation signals are filtered by filters that represent the vocal tract transfer function. A warping factor, which can be set in the user interface, can then also be applied to the filter coefficients to effectively shorten or lengthen the vocal tract. The frequencies of the poles are warped by performing a bilinear transformation in the Z domain, and this involves transforming the filter coefficients through the substitution of a unit delay filter with an all-pass filter. The unvoiced excitation is filtered using filter coefficients and gain values obtained from regular LPC analysis, and then the final speech signal is created by combining the voiced and unvoiced signals. So now that I've described the system, I'll go into how we tested it through a manipulation task-based listening test. So for this listening test, we took an all-voiced utterance "We were away a day ago" in broad focus, spoken by a male Irish English speaker, and this utterance was then analysed and parameterized using the GlórCáil analysis stage. The mean F0 of the utterance was 104 Hz, and the mean RD was 0.94. Baseline stimulus was resynthesized in GlórCáil using the F0 and RD contours. Baseline stimulus was modified by the participants in the listening test using a purpose-built interface. Now I'll discuss the interface we used in this particular test. So we used this layout for the test, but the GlórCáil system can incorporate a wide range of GUIs, as there are a small number of transparent input and output parameters to the other stages. So 3 parameters were manipulated: RD, F0, and the length of the vocal tract, VT. Parameters were represented in the interface by sliding blocks labeled voice, pitch, and size, and dragging the blocks up and down controlled parameter scaling factors. RD and F0 contours were multiplied by the obtained RD and F0 scaling factors, and the VT slider directly controlled a warping coefficient that was applied to the entire utterance. The RD scaling factor ranged from between 0.5 and 2, so that the baseline values could be halved or doubled at either end of the scale. Constraints were also applied so that the RD values remained inside the usual range of 0.3 and 2.7. The F0 scaling factor ranged between 0.7 and 3, as this approximated the range of F0 values from adult male to child. And the vocal tract warping factor ranged from between minus 0.1 and plus 0.1, with negative values effectively simulating a shortening of the vocal tract and positive values a lengthening. So a listening test was carried out using the interface. 16 participants took part in the test. They were all native English speakers, and the baseline sentence had to be manipulated by the participants 9 times to produce 9 utterances, 3 speakers by 3 affects. So all combinations of man, woman, and child with angry, sad, and no emotion. 2 more utterances were included at the beginning of the test to allow participants to familiarize themselves with the procedure. The results from these were discarded. The participants were allowed to listen to the results of their manipulations and make changes as many times as they wished. The stimuli were presented through high-quality closed-back headphones in a quiet environment, and the test took approximately 10 minutes to complete. So what we expected from the results, based on a review of the literature, was that increasingly high F0 scaling would be used or would be required for speaker transformation to woman and child. No emotion baseline to woman transformation would require shifts to breathier phonation, in other words, higher RD scaling factors. For SAD in all target speakers, a higher RD scaling factor would be used, corresponding to breathier, laxer phonation. For angry in all target speakers, a lower RD scaling factor would be used, corresponding to tenser phonation. There would be a negative vocal tract warping factor used for woman and child transformations. And finally, angry voice in all target speakers would entail a positive vocal tract warping, meaning a longer vocal tract. So mixed model analysis of the results of the listening test were performed in R to test if the scaling factors varied significantly across target speakers and affects. Step-down model simplification was carried out to eliminate non-significant effects and denominator degrees of freedom. The models were fitted using the maximum likelihood method, and the initial model included target speaker and affect as the main predictors, as well as their interactions, and random effects included bi-subject random intercepts. So here's a full table of the model outputs and their associated figures. I'm not going to go into the table, but let's have a look at the figures. So taking a closer look at these figures, you can see that RD scaling did not vary significantly across target speakers. However, significant effects of affect was found. RD scaling was significantly higher in SAD, breathier voice, and significantly lower in angry, tenser voice for all speakers. For F0, scaling was significantly different across all speakers and no emotion, making it unsurprisingly a useful parameter for speaker differentiation, so between man, woman, child. The same relationship held also for angry. A significant target speaker by affect interaction effect was also found for F0 scaling. In angry, the F0 scaling factor was significantly higher for a child target speaker than for woman. In SAD, this differentiation was not observed, and affect was not a significant predictor of F0 variation in man. In the child target speaker, angry affect required higher F0 scaling than SAD, and in the woman target speaker, a similar trend was not significant. As expected, target speaker was a significant predictor of the vocal tract warping factors. These were significantly higher for man than for woman and child in all affects, and significantly larger for woman than for child, except in the no emotion condition. A significant target speaker by affect interaction effect was found. Vocal tract warping factor did not vary with affect in woman and child, but was significantly higher for the man target speaker in angry compared to SAD and compared to no emotion. So just looking at the hypotheses, two of our hypotheses did not pan out when compared to the findings, and those were that there was no clear shift to breathier voice for a woman with no emotion, and that angry voices did not have a positive vocal tract warping, except for the case of man. So just to summarize the results, F0 and VT, the vocal tract warping factor, were found to be significant predictors of speaker and gender/age, but not for affect, except in the case of VT in angry man. RD was a significant predictor of affect, but not of speaker identity, and significant interactions of target speaker and affect were found for F0 and VT. So just in conclusion, the goal of the test reported here was to confirm that the GlórCáil system parameter manipulations can generate speech with gender/age specific characteristics and affected coloring. The range of target speakers and affects that were specified for this voice transformation task were limited, but was deemed sufficient as a proof of concept in the initial evaluation of the system. The parameters that the system allows to control prove useful in modulating linguistic and paralinguistic prosody characteristics in earlier studies, as well as in this study, and the parameters appear to work in combination, and manipulations performed by the participants were mainly in expected directions. So just as future work, the scaling factors values from this experiment will be used to generate stimuli to test the proposed system when it is integrated into a DNN-based speech synthesis system as part of the ongoing work of the Ailbhe project. But this, in fact, has already been done as part of my PhD thesis, and this will hopefully be presented at InterSpeech. So thank you very much.